Welcome back to Unit 8, Video 2. Our goal for today, given an exponential function, you'll be able to understand how it grows and graph it. Okay, to help you understand an exponential function, we're going to start today with a little story. All right, so here we go. Our story for today. Congratulations! You've just gotten your first job. It's only for 1 month, 31 days. And you have 2 payment options. So option number 1 for your very first job, you can earn 1 penny on the first day, and then you can double it every day for a month. That's called the penny plan. Or option number 2, you could take a 1 lump sum of $1 million. So which would you choose? The penny plan or the $1 million? All right, well, let's see. All right, so $1 million definitely sounds like a lot of money, and that's really easy for us to visualize in our head, $1 million. All right, so let's go back and let's revisit the idea of the penny plan. So for this penny plan, day 1 we get 1 penny, day 2 we get 2 pennies, day 3 we get 4, then 8, 16, 32, 64, $1.28, $2.56, and on day 10, $5.12. So every day it doubles. So have you changed your mind yet? $1 million or the penny plan? Well, 10 days, there's still a lot to go in the month. So let's take a look here. So day 11, 12, 13, 14, 15, if we double our amount every day, day 15, $163.84. We're getting there. That's still not a lot of money for 15 days of work. Let's take a look. Keep on going. All right. So now on day 20, ooh, look at this. Now we're at $5,242.88. Still not quite $1 million, but we are growing quite a bit. So have you changed your mind yet? $1 million or a penny plan? Let's see. We're at 5,000 on day 20. Ooh, it's getting a little scary. $1 million is a long ways away. Let's see what happens now. Day 21, we're going to double it. We get $10,485. Day 22, we double it. Now we're at almost 21,000. Day 23, day 24, we're doubling it every day. Doubling it again. Now we're at $167,000 on day 25. We got 6 days to go. All right, day 26. Day 27. Uh-oh. What happens when you double $671,000? Day 28. We've made it $1,342,177.28. And we still have 3 days to go. Day 29. Day 30. Day 31. If you picked the penny plan, you have just earned yourself $10,737,418.24. You have changed pennies into millions by doubling your amount every day. All right, so now, would you tell someone confidently that you would pick the penny plan? I sure hope so. So this penny plan, we started from pennies, something that you didn't think was a lot of money, and we were able to grow it within 31 days into $10 million. So think, did you change your value slowly? Did you change it rapidly, or did it change as you went along? Well, this is what we call exponential growth. Exponential growth is when a population or a group of something is growing and the increase is non-linear. It becomes more rapid in proportion to the growing total number of size. All right, so this is an example of our pennies. This is what happened. Day 1, day 2, day 3, day 4, day 5, day 6, day 7. We were so little, and then all of a sudden, we got up to like day 15. Day 20, and it started to grow really fast. Okay, this is what we call an exponential function, where it grows slowly and then it grows more rapidly. And the reason why we call it an exponential function is because look where your x is. Your variable is now in the power. So it's AB raised to the power of x. x. And ladies and gentlemen, this is what we're going to be looking at today, this idea of exponential growth. All right, so we're going to go back to our note sheet now. So our idea of exponentials. So hopefully you would pick now the penny plan. All right, we're not going to be looking at that YouTube website at the bottom. All right, so let's go ahead and talk a little bit about exponential growth. So exponential growth is like we had in the PowerPoint there. It's going to grow at a nonlinear rate. It's going to grow slowly, and then it's going to grow more rapidly. Well, we can have exponential growth, or we can have exponential, and oops, there's a typo here. We can also have exponential, and this one is going to be called decay. Exponential decay. And that is when a population or a group of something is declining. It is decreasing at a non-linear rate, non-constant, which ever more slow in proportion to the decreasing total number of or size. So it's going to decrease fast, and then it's going to decrease slower. Okay, so graphing exponential. Oh, there's another typo. I lost my P there. So graphing exponential functions. So an exponential function with base b is defined by the following. F of x equals a b raised to the x. So in this formula, a is the initial amount, the amount that you start with, and b is the rate of decay or growth. Okay, so b always has to be greater than 0, and it cannot be equal to 1. All right, so let's take a look here, okay, at our different types. So exponential growth is when you grow slowly and then it grows very rapidly. Exponential decay is when you start off decreasing fast and then it gets slower and slower and slower. Okay, also with exponential functions, we're going to have something called an asymptote. So you can go ahead and chuckle at that name, but that's really what it is. Now, an asymptote is essentially an invisible line that the graphed function will approach very closely, but it will never touch. So if I look at this curve, it looks like it's getting closer and closer and closer to this dotted line, but it's never quite getting there. It's just kind of leveling off. Okay, so that's what we would call an asymptote. All right, let's go ahead and let's take a look. So our penny example was an example of exponential growth. We're going to take a look now at an example of exponential decay. All right, so here we go. In chemistry, the radioactive elements break down exponentially. A scientist started with 320 grams of the radioactive Koeppel-Keenan element, which had a decay rate of 1/2 every day. The life of the radioactive element in this experiment can be modeled as f of t equals 320, your initial amount, with a rate of 1/2 raised to the t, where t represents days. Use the graph below to represent this function. So we want to go ahead and we want to graph this function. So here we have f of t and t. So your t is where your x usually goes. So that means my x-axis is going to be time, okay? And then my y-axis, so we're talking about the radioactive element, okay? So this is the number of grams. So number of grams of the element is our y value, okay? So let's go ahead. We want to set up a table of values to figure this out. Well, just like we did in yesterday's lesson where we were working with our absolute value functions, we're going to let the calculator also help us with exponential functions. So to graph this, to find our points that we want to plot, we're going to go ahead and go to y equals, and we're going to type it in. So 320 parentheses. Now for my fraction, I'm going to do alpha y equals and go to fraction. So 1/2. And my parentheses, and then raised to the, now this is a t, but we're going to use an x in the calculator. All right, and then we're going to go to our table of values. Now, we do not want negative x's because our x's is time, or in our time in this case is going to be days, and we can't have negative days. So we're going to start here at 0, and we're at 320. And then at 1, we're at 160. At 2, we're at 80. at 3, we're at 40. So it looks like every day we're going down by 1/2. So let's see, day 5, we're at 10. Day 6, we're at 5. Day 7, we're at 5 halves, which is 2.5. All right, then we're at day 8, which is going to be 5 divided by 4, so 1.25. All right, and then 9, we're going to be at, oh, so what's happening here is it's keeping fractions because I put a fraction here. But if I change this now, all right, and I make that a decimal, 0.5 raised to the t, now I believe it will give me decimals. There we go. So now we're at 9 is going to be 0.625. 10 is going to be 0.3125. Now I'm going to keep going. If we take a look here though, my numbers keep getting smaller and smaller and smaller, but are they ever going below 0? So this is 6.1 times 10 to the negative 4. So these are getting really, really small, but they're never actually becoming 0. So now we want to go ahead and we want to graph this. Now we have to remember that with graphing, we might have to find a new scale. So we might not be able to count, okay, simply by ones going up for our grams. So we need to go from 320 all the way down to approximately 0. So 1. So I know because I counted this ahead of time that in order to get all the way to the 320, I'm going to have to count by a number larger than 10. So I'm going to go ahead and pick 20s. So 20, 40, 60, 80, 100. 120, 140, 160, 180, 200. 220, 240, 260, 280, 300, and then 320. All right, and then my days, I'm going to simply just count by ones. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so let's take a look. At time 0, we're at 320. Okay, at day 1, we're at 160. Day 2, we're going to be at 80. Day 3, we're at 40. Day 4, we're at 20. Day 5, we're at 10. And then day 6, we're at 5. And then we're getting closer and closer. But remember, if you take half of something, you're never quite getting to 0. You're just going half of the way. So we start here, and we're going to go down. And with exponential, sometimes you're going to have to estimate your points, and this goes on forever, hovering right above the x-axis. Okay, so for this question, is there a horizontal asymptote? Is there a line that this is never going to go below? Well, it's never going to go below the x-axis because you cannot have negative grams of a substance. Is this exponential growth or exponential decay? Well, let's take a look. Are we going up or down? We're going down, so this one would be decay. What is the y-intercept? Do we have a y-intercept? Yep, it crosses at 320. So if we wanted to put that as a point, it would be 0, 320. And is there an x-intercept? Is this ever going below the x-axis? Nope, so there is indeed none. So ladies and gentlemen, this is how we graph an exponential function. Okay, so we're going to flip it over. So one more part for today, and that is finding the equation of our exponentials. Now, just like we did linear regression, quadratic regression, we can also do what's called exponential regression. So to do this, you need to have at least 3 points, and then we're going to use the function exponential regression in the calculator. So if we take a look here, we have our x values and our y values, and we're going to look at the relationship. So our x's are going down by 1 each time. Now if we look here, we're going up by 0.75, we're going up by 3, up by 12, and up by more than 12. So if we take a look, we're growing, and we're growing at a non-constant rate. So that means this is going to be quadratic. So I'm going to go ahead in my calculator, and I'm going to type this in. So stat, edit, and now we're going to go ahead and type this into our lists. Okay, once we have it, then we're going to go stat, calculate, and now I'm going to go down, and this is going to be option number 0, exponential regression. I go down to calculate, and here we go. So this function is going to be y equals 1 and then 0.25 raised to the x, and we've got it. All right, ladies and gentlemen, for homework, you're going to flip the page over and try the next few questions on your own and turn them in